So, hello guys. What we are gonna talk about today is all about normal stress. Normal stress is the stress when a material is subjected to a load which is perpendicular to the cross-sectional area. This is what we call normal stress. There are different types of stress, like shearing and bearing stress. But those type of stresses will be answered or discussed later on after understanding the most simple or the normal stress. So we know that normal stress is load over area. The most common units for load are newtons, kilonewtons, pounds, and kilopounds. These are common units. As for area, it should be millimeter squared, meter squared, inch squared, and feet squared. These are common units used. As for sigma, there are unit of Pascal, which is equals to Newton per meter squared, and megapascal, which is equal to Newton per millimeter squared. Newton per millimeter squared. So our first problem. A hollow steel tube with an inside diameter of 100 mm must carry a tensile load of 400 kN. Determine the outside diameter of the tube if the stress is limited to 120 meganewton per meter squared. So first, let us draw the figure. This is the outside circle. So if we project to the left, we will have the 100 millimeter inside diameter, and to the right, projecting to the right, we would have a diameter of unknown length. So here is the body. Let me draw first. So the hollow tube is subjected to a downward force of 400 kilonewtons. By the way, a hollow tube is the same as a hose, which has empty inside. It is empty inside. So first, we will write the given on this side. Given. Our first given is the 120 meganewton per meter squared. First, let us recall the equivalent of this. Kilo is equals to 10 raised to 3 or 1,000, and mega is equals to 10 raised to 6, and giga is equals to 10 raised to 9. So observing the given unit for our stress, it is meganewton per meter squared, but pascals or megapascal is not under that unit. So we need to prove or to know what is it equal to. So we know that megapascals is equal to Newton per millimeter squared. Multiplying it to meter square millimeter squared over meter squared. So the ratio for meter and millimeter is 1000. Take note that it is raised to 2. So 1000, which is 10 raised to 3 raised to 2, is equals to 10 raised to 6. Now we know that the value of mega Newton is 10 raised to 6. So if we cancel the same units, Newton, so the 10 raised to 6 and Newton, we will have mega Newton per meter squared. So we know that mega Newton per meter squared is equals to megapascal. So rewriting it is equals to megapascal. Our next given is the 400 kilonewton load, the normal load. So we know that a kilo is 10 raised to 3 and our load is under kilonewton. So we need to transform the kilonewton to newton to match our value of megapascal on our stress. So our area, the cross-section area, is of course a circle, a hollow tube. A hollow tube is a circle area of the big circle minus the small circle. So factoring out pi over 4, we would have pi over 4 d squared, big letter d squared, minus small letter d squared. Next is to write the given. So we have 120 megapascals. Let's write the units, is equals to, so we converted it 400 multiplied to 10 raised to 3 Newton over the area. So pi over 4 multiplied to, so unknown d squared, big letter d squared, minus given to 100 squared. So algebra, 120 times 1/4 is 30. So meron tayong pi. Let's cancel out the unit para hindi pa ulit-ulit. So d squared minus 100 squared equals 400 multiplied to 10 raised to 3. So type nyo lang our diameter is equals to 119 and 35. So our unit, let's check, since you have megapascal, so it should be millimeter squared. But if we square it, we will have only millimeter. Next problem. So a homogeneous 800 kg bar AB is supported at either end by a cable as shown in figure P-105. Calculate the smallest area of each cable if the stress is not to exceed 90 megapascal in bronze and 120 megapascal in steel. First, let us draw. So this is the supports. This so let me draw it first. Going down. So medyo nasobrahan. Hindi naman siguro kayo magagalit. Going. This is the cable still. So we need to understand that cables are tension and forces. They are used for their forces are pulled. They are going away from the object. So example is when we strap a rope. Cable has the same properties as a rope. If we strap it on an object, you cannot move the object by pushing, right? It will not move. But if you pull it, the rope will be in tension, causing the object to move along. So we have a given of 800 kilogram mass, and we know that weight is equals to mass multiplied to the force of gravity, mg, Wmg. Weight is 800 kilogram multiplied to 9.81 meters per second squared. So we know that we should note that Newton is equal to kilogram multiplied to meter per second squared. Weight is, the value is 7848 newtons. So since we have a symmetrical problem and the rigid bar, so we assume that the resultant force of the rigid bar is at its center. So we can solve this by using the axial. So we will use the axial force diagram to determine if the structure is really in equilibrium, because that is what we are aiming for. Diagram. So at it joints we would have going down is, so since our cables are in tension, they will have to be in the direction away from the cable, and the rigid bar, when subjected to gravity, will be going down, and its resultant force is of course at the middle. So we have the value of W as 7,848. So we know that when it is symmetrical, the forces on the cables are equally distributed at the sides. So the tension on the bronze will be the half of the weight of the bar, right? So when we move from the bronze to the middle part, there are no loadings, so we have a constant force until the middle. But at the middle part we have a negative 7,848. Negative because it is going downward. So it is, of course, the negative. It was negative 3924, and it is constant until reaching the steel cable. And lastly, going up is the 3,924 value of steel, closing the diagram, making it in equilibrium. So let me shade. So the forces that are going up are positive and going down are negative. It is a very simple graph. So if the stress is not to exceed 90 megapascal in bronze, so we would have a stress in bronze BR is equals to 90 megapascal MB, and the stress on the steel is equals to 120 megapascal. So megapascal. So recalling our formula, so the unit strength, the axial strength, is equals to sigma over equals load over area. So on the bronze, Q sigma BR, so load BR, that's the load BR over area of the BR or bronze. Note that we have here 90 megapascal and its load of 3,124 newtons. So checking the units, it's in Newton and sigma is in megapascal, so it is correct. We are looking for the area. We have millimeter squared, so just type it, put it up and put the MPa down. You can cancel the Newton there, leaving only millimeter squared. 43.6 millimeter squared. That is our area. Next would be for the steel. So the same for steel. Let's write it. For steel, sigma steel equals load of steel. The normal load, the load that is perpendicular to the area, the cross-sectional area. We have a limit of 120 megapascals equals the loading, which is the same 3924 Newton per area of steel. The unit is also in millimeter. So writing it down. By the way, that is the location of the area that we are talking about. Area is equals to 32.7 millimeter squared. We are done. So let's put it in a box for easier identification. No, that is all for this problem. Thank you and God bless. By the way, these are sports.